here.
Can you see something?
Yes.
Okay.
All right. So let me just get the introduction. So our next speaker is Timour Paltashev and Trinayan Baruah. So Timour is working at AMD Raytheon Technology Group and has over 23 years of experience in Silicon Valley. He holds a PhD and a Doctor of Technical Sciences, and he has worked in exascale supercomputing, visual graphics, perception, deep learning, and so on. Trinayan is a GPU architect at AMD, where he currently works on architecture and design of the AMD Instinct line of products. And he earned his PhD at Northeastern in 2021. So with that, take it away.
Thank you very much for introduction. So sorry, we just could not come physically visit because of a short notice and complications with travel arrangements in such short time. Derek supposed to be here. He is actually one hour drive probably from Montreal, but also he has like his family event conflict. Basically, we try with Trinayan to cover this topic, because basically we just talk about like AI HPC innovation, marketing, application support, Infinity Hub, which actually support our customers, frameworks and libraries support, scalability, programming languages for application porting to our platform. And Trinayan will discuss in details accelerate computing with HIT textbook project. And this textbook was printed at the end of December, and also go in details on the chapters, what he just directly written, and describe what actually will happen in the future, because it's live project and it will be evolving along with Radeon Open Compute ecosystem. And okay, so we just thought that AMD ROCm software ecosystem is critical to enable all user applications, and we have like two target use cases. This is supercomputing and HPC, and basically thanks to Department of Energy and supercomputing projects, exascale supercomputing project, we've first built machine like Frontier on Oak Ridge National Lab, and this year we're building machine for Livermore National Lab, and those machines are definitely like give us like significant push ahead like in this domain. And another driver is artificial intelligence and machine learning applications. And so basically we just interact with major providers and work with optimized tools, libraries, and frameworks for both HPC and AI. And a lot of them are ready today. And so basically what we're doing, we just mostly mirroring all the activity of our major competitor and providing all the tools for toolchain, compiler, debugger, profiler. I worked with this team like last 4 years. We have libraries also. This is part of our activity as well. NAV communication, and we have like all libraries supporting machine learning, similar to CUDNN and others. We have like driver runtime on ROCm, which actually support activity on different versions of Linux operation systems. And we have several support tools and system management. And basically, we just very actively interact with open source community and third-party contributors, because ROCm is open source ecosystem, and we're just embedding everything, whatever just was it's possible in HPC and AI professional world. Below is like some versions of implementations when we have like big giant supercomputer in Oak Ridge like built, and this is like accelerator of different parts, and this is like new versions of accelerators like servers in general. Like it's possible to get like AMD ROCm on different kind of like starting from desktop with high-end GPU card, Radeon GPU card, and ending like big giant supercomputer with 9,000 nodes like we have on Oak Ridge. And application support, because this is like new platform AMD. We're just talking about MI, and we're behind on this application domain versus our respected competitors. We just helping to move all of those applications, existing applications, to our GPU platform. We just have at the moment 60 applications supported, and we have like on performance leadership on key applications, because we're not only migrating to our platform, we're also providing the superior performance in this stuff. And also expanding now our focus, because before it was like significantly targeted to HPC and AI market related to like the very big customers, including government ones. Now we just also targeting commercial HPC segment, and also work with multiple ISVs to bring more and more applications to the ROCm ecosystem. So if you want to know all of the details, you can go to AMD Infinity Hub on this location. And so basically we have like all information about MI200's product family support. And when we have like new product family coming like at the end of this, like the second half of the year, like you will have like another number over here, not MI200, MI300. And so we have like also whole applications, tables, performance results, everything, comparison of there to check like how you can check get your application moved to our platform. So for machine learning frameworks, so we work like with big vendors. So PyTorch supported in partnership with Meta. This is like a process for years, and we use our platform and like full support of this stuff. Same as like with TensorFlow, and we have Jack support, and our last one is upstreaming, because FreeFirst already available upstream version, and we have OpenAI Triton intermediate representation. So this thing also is going. Everything works in open source code. Yeah, if we just take, this is like simple steps, like how PyTorch and model should be adopted, right? And in general, more than 2,000 operators tested, it works. Over here we have ROCm 5.2. So we have like current release, we have 5.4. Usually we have like one step behind, like 5.3, 5.2 on the support of the frameworks, because it takes time to check and optimize with every new version of the ROCm. Okay, and important features we have, like we're able to use the model trained on NVIDIA hardware for inference stage on AMD, so basically, and vice versa. So that's why there's both users NVIDIA and NVIDIA hardware, they can symmetrically use AMD hardware. So major thing is like when we just was working with national labs on supercomputing project, like bring up all of those libraries existing on NVIDIA platform to work in highly efficiently on our platform. So basically we have like for every NVIDIA library, we have mirroring ROCm libraries, and both libraries provides exactly the same functionality and with competitive performance. And we have like math libraries, we have communication libraries, we have C core, C++ core libraries, and we have our wave matrix multiplier libraries, and most important for artificial intelligence like CUDNN, we have MI open library, and highly optimized. Sometimes like we have like problems using this stuff, because when you run the kernel, which use like 98%, over 98% LU utilization, you have like problem with power supply stability. And frameworks, because we have like high performance computing frameworks, Caucus, Raja, which actually comes request from national labs, and we have like other frameworks and libraries. They also support it, and we significantly invest significant funding to help our mostly academic partners who just work with those libraries and bring them from NVIDIA platform to HIP platform. And so this is like basically scalability. We have full support of scalabilities with for machine learning frameworks and HPC applications, and message passing interface supported in different forms. We have open MPI, we support this library in Vapid, and we have also support HP, Cray MPI, Fabric. So, and also supported all of the physical interfaces that we have, Ethernet, Slingshot, InfiniBand. And so this system is scalable on dimensions. So basically, we're just talking about current system on Oak Ridge. It's like 9,000 nodes, over 72,000 GPU cores working simultaneously. And so this is like the size of the system maximum physically existing at the moment. And when we have machine in Livermore, it will be even bigger because it's just significantly more powerful. Okay, so we support like multiple programming languages. So basically, we're just talking about CUDA because we can convert any code from CUDA to Hipify, and we have like support over Fortran code over there. We have HIP4. So we have CSSL support, and we have OpenACC, OpenMP, OpenCL, standard not supported, so Python and Julia also. So in general, we're just talking about portability with multiple applications on multiple languages. And so I'm finishing right now, and we'll disconnect because I need to go, and Trinayan will continue. Thank you.
Yeah. Thank you, Timour. I'll start sharing my screen.
Okay, we can see it.
Okay. Can you see it now?
Yep.
Okay, thanks. Yeah, thanks for the introduction. And I'll just be covering a brief about our textbook that we recently published in collaboration with Northeastern University and William and Mary, and also with support from some third-party partners as well as AMD internal tools and compilers team. So the book is titled Accelerated Computing with HIP. And so in basically, generally the book is, can be categorized in two parts. The first is, of course, like talking about the HIP programming language itself. So how do you write a basic program, as well as, what kind of tools and libraries are available. And then we also have a good chunk of the book section dedicated to tools and profilers, and as well as third-party tools. So the language itself, it's has all the necessary support for GPU programming, including libraries such as BLAS, FFT, something that Timour already covered in the previous slides. So why did we decide to write this book? The first is that there's a lack of a HIP programming textbook, and given that AMD is now positioned well in the compute market as well, so it would be given that many industries have also AMD GPUs as well as national labs and universities. So this book will help students who are just starting to learn GPU programming to get familiar with how to program using HIP. Right. And so we cover both the hardware and the software concepts, how to write a kernel, as well as some of the architecture aspects of the GPU that is necessary to understand how you can write high performance code. And in the book, we cover a wide range of programming examples so that the reader or the student who is reading the book can get used to different concepts in GPU programming, such as divergence, as well as shared memory uses, and any of those kind of optimizations. And to facilitate more performance tuning, we also cover numerous tools that can help the programmer achieve high performance on these GPUs. So just a brief introduction, HIP is like the main platform or language of choice when running on AMD GPUs today. And it provides a rich set of APIs by which you can communicate and launch work to the GPU. So the syntax is very similar to the traditional GPU programming languages such as OpenCL and CUDA, though it is less verbose than OpenCL. So in that aspect, it is very similar to CUDA. And there are similar APIs that you would normally, for anyone familiar with CUDA, would be used to, such as CUDA malloc, hip malloc, CUDA memcopy, hip memcopy, and so on. And then talking about the general ROCm software stack itself, right? So HIP is just the programming language, but then we have multiple layers of this software stack that ROCm provides. So on the top level, we have, of course, the frameworks, and then we have libraries such as the ROCm libraries, as well as MIOpen, which is a substitute for CUDNN. And then internally, we have the programming model language itself, like HIP and OpenCL, though HIP is now the platform of choice. And then we have the intermediate runtimes compilers such as HipClang, and then finally the runtime layer, which is the ROCm layer. And to facilitate performance tuning, we have multiple programmer and system tools that enable performance optimization. So the book is basically divided into 11 chapters and 2 appendix. So it's about 208 pages. It's featured a nice forward by Jack Dongara, and some of the important components of the book are, of course, as I mentioned, like the syntax of how to write a HIP program. This is especially useful for someone who is very new to GPU programming. But there are other advanced topics as well. For example, how to write assembly code that is targeted for AMD GPUs. And in the book, we mainly cover the MI100, which is the AMD's Instinct line of products that is used in data centers. And so we covered the GPU architecture of that and how we can think about the architecture when writing programs. So this is the breakdown of the chapters. So we start off with relatively simple stuff like basic syntax as well as the architecture. Then we cover some of the more advanced topics, such as some useful programming patterns, as well as optimization, such as how to use shared memory, how to leverage HIP streams. Then we have a large chapter dedicated to the different ROCm libraries. For example, the BLAS, FFT, sparse on those libraries, so that programmers who are relatively familiar with the basics can start leveraging these libraries. We also have a chapter dedicated to how you can take a CUDA program and port it to HIP. So there's a rich set of tools, especially through HipClang, that is developed by our internal teams, and this allows to take very complex applications that are written in CUDA today and convert it to HIP. And then we have chapters on multi-GPU programming, as well as certain third-party tools. So the third-party tools chapter has numerous open source HPC tools such as PAPI, Scorpy, Trace Compass, and so these chapters were contributed by our partners who developed these tools. So in this brief presentation, I'll just be covering the multi-GPU programming chapter briefly, just to show the kind of things that we have in the textbook. So as we know, like multi-GPU systems are today very pervasive in a plethora of computing domains such as HPC and AI. And the reason is that single GPUs are no longer sufficient to satisfy the demand of many of today's applications. So ROCm and HIP provides capabilities to write multi-GPU applications seamlessly via various mechanisms, as we'll see later. So in this chapter, or in this section today, we'll basically see how some of these common patterns are and how we can leverage them. So the high-level API is that we use the HIP provided APIs to control the GPU and then run tasks on it in parallel. And to do that, we have multiple options. The first is HIP streams, which is basically you can control each GPU via an independent stream, or the other option is to use CPU threads, which is basically P threads or an C++ thread abstraction that you can use to control the different GPUs. Then coming on the more other framework side, we have support for MPI and RCCL. So these approaches can be combined together. For example, you can use 2 CPU threads to control 4 GPUs, And within each thread, you can use HIP streams for each GPU to increase the device level concurrency itself. So the key idea in the stream-based multi-GPU programming, which is something we cover in this book, is that task enqueued in different streams can execute in parallel. So one of the programming pattern that we cover in the book is basically you create a stream for each GPU, you perform all your declarations and memory allocations, and you launch your kernels, and then you synchronize at end. So in the textbook, to simplify the explanation, we basically just have a very simple vector addition across GPUs, with each GPU working on a chunk of the input. So that's like a data parallel paradigm of multi-GPU programming. So here we have a simple example, and some of these parts are commented out in view of the slides itself. But the main idea is that first you have this loop where you are setting each device that you have in your system, and then you are doing things like creating streams, assigning buffers, and then doing your memory copies. Then the next part is to launch the kernels on each of these GPUs. So we are, again, have this for loop where we are setting each device and then launching the kernels on that stream that is associated with the device. Finally, we synchronize at the end, and then we copy the data back to the host. So this is a simple way on how you can think about writing a very simple data parallel application for multi-GPUs using HIP streams. Now, ROCm itself, like the framework in general, supports multiple modes of cross-GPU communication. So some of the main approaches are, like, first of all, the explicit memory copies from GPU to GPU, which is device to device using HIP memcopy. So this can either use P2P or via host memcopy, depending on the support that is there on the hardware support that is there on the device. And there's of course the direct cache access that enables to someone to just write a that simplifies the GPU programming, because then you don't need to explicitly do memory copies. You can access memory on the other device via simple pointer semantics. And so this allows, sometimes it may not be good for performance because it has bandwidth implications, but oftentimes it simplifies the programming mechanism, and so that's something that we cover in the book. And the other part that ROCm supports today is like unified memory, but that is something that is not covered in the current version of the textbook, which we plan to cover in the next release of the book. So just giving a high-level overview of P2P memcopy versus the direct cache access mechanism. So there are benefits and pros and cons of both of these two approaches. So the P2P memcopy, where you just copy from device to device, it basically doesn't enable you to do any fine-grained data sharing. Even if you transfer a single line, you still have to call the API and set all that up. So that's not a good programming practice in general. But with the direct cache access mechanism, it enables very fine-grained data sharing, because you can basically access memory on other device without having to call any special APIs. In terms of bandwidth utilization, because the P2P memcopy, traditionally is done to do like bulk memory copies, so it has high bandwidth utilization. But direct cache access, because sometimes you are accessing very small amount of data on the other device, your bandwidth utilization may be very low. Coming to the programming use, the memcopy, you have to call the API every time you want to do it, and that has an extra cost. But the direct cache access is very simple. It's almost as if your memory is on your GPU, so you're just basically accessing the other device. And then compute communication overlap is easier to do with the direct cache access mechanism, just because of the way that you don't have to deal with API calls and synchronization and all those kind of factors there. So in the book, we cover code examples on how to use each of these approaches when doing communication across GPUs. And now the last part is that I'm covering is the ROCm collective communications library. So this is a very common library that is used by many frameworks such as PyTorch for multi-GPU system communication. And it provides a very common MPI style interface with support for many primitives such as all reduce, gather, scatter, reduce, broadcast. So these are some of the common primitives that are used in many of the machine learning workloads. So the thing with RCCL is that it's a topology-aware library. So it's optimized for AMD GPU systems. And in the textbook, we cover RCCL and how to use it. with two main examples. The first is basically we broadcast the data to multiple GPUs and then calculate the average of the result, from by the multiple GPUs. And we have numerous examples to illustrate how to do that in the textbook. So here, coming at a simple example, and then looking at this program, first we are like defining our buffers and communicators. Then, if from the rank 0 of that particular program, whichever device is associated with it, we are broadcasting the ID so that the other ranks can also bind to that communicator. And then we are initializing the communicators, creating the streams. And with Nickel or RICL, we don't have to write a specific kernel because it already provides support for these basic primitives. So here we are just calling all reduce on the data. So it will automatically launch the necessary kernels because it's provided as part of the library. And then it will finish the all reduce and then finally synchronize on the stream. So one thing to note is that RICL uses the same API call as Nickel, which is the counterpart in NVIDIA. So we don't have to replace the NCCL with RCCL. It uses basically the same programming syntax. So further activity, we are, of course, working on covering more tools that are new. For example, AMD recently launched OmniPerf, which is a profiling tool that is much more intuitive and easy to use compared to the current profilers that we have, like ROCperf. And then we are also, extending support for other components such as unified memory that I mentioned. And there's also supporting material that will be developed as part of this project. So that would include things such as slides and video tutorials. So that's something that university students or people who are new to GPU programming can use. We're also looking at translation to other languages such as Chinese and Russian. And so that's like the next steps in the roadmap. With that, I'd like to thank everyone for attending. And if you have any questions, let me know.
Thank you for that great talk. Does anyone in the audience have any questions or any of our participants online? No. Okay. So I have a quick question.
Yeah, sure.
Another tool that's useful for a lot of programmers is dynamic binary instrumentation tools. Does AMD have any of these type of tools for HIP